Welcome back to the deep dive.
Great to be back.
Today, we're taking a really fascinating leap. We've explored the why and the mind-bending physics of quantum computing before, what qubits are, how they behave.
Right, the foundational concepts,
Yeah.
superposition, entanglement.
Exactly. But now it's time to shift gears a bit. We're going from pondering the quantum realm to becoming, quantum architects ourselves.
Yeah, moving from the what to the how. From principles to actual building blocks. This is where the engineering side really starts to, meet the quantum magic.
Absolutely. Our mission today is understanding the how. How are individual qubits precisely controlled? How do they combine into these powerful multi-qubit systems? And crucially, how is this whole process just fundamentally different from classical computing?
It really is a different way of thinking about computation.
We're stepping into the precise and controlled world of quantum gates and circuits, the fundamental, let's say, verbs and blueprints for quantum algorithms. It's a really cool intersection of theory and practical design.
Couldn't agree more.
So get ready to sort of build with us. We'll explore what exactly are quantum gates and how do they control qubits. We'll look at the poly gates, specifically the X gate. What's this phase flip with the Z gate and why is quantum phase so important?
And the Hadamard gate, why is that one so crucial?
Right. And the S and T gates, what about universality? Then, moving to multiple qubits, what's the controlled NOT or CNOT gate? How does it create entanglement from superposition?
We'll also need to touch on the math, like the tensor product for describing these multi-qubit systems.
Definitely. And how do we visualize all this? How do we read a quantum circuit diagram? We'll walk through building a simple circuit, like for a Bell state.
Yeah, classic example.
Then there's this big idea. Reversibility. What does that mean? Why are classical gates mostly irreversible, and why is that a problem? How does quantum reversibility offer an advantage?
It's a fundamental difference.
We'll try to summarize how gates, circuits, and reversibility form this whole quantum architecture. And finally, if classical gates like A and D are irreversible, how can a quantum computer do everything a classical one can? What's the Toffoli gate?
That's a key piece for connecting the two worlds.
Okay, let's dive in. So if qubits are our basic units, how do we actually do anything with them? What are these quantum gates?
Okay, so think of quantum gates as the fundamental operations in quantum computing. They're kind of the verbs that act on qubits. It's analogous to the A and D or R gates you'd find in your classical computer shell.
Right, the logic gates.
Exactly. But here's a key difference. They aren't fixed physical circuits in the same way. Quantum gates are actually precisely controlled physical operations. We're usually talking about things like targeted pulses of microwaves or lasers or magnetic fields.
Ah, so it's an external manipulation.
Precisely. Yeah. And they don't just flip a 0 to a 1, they manipulate the quantum state itself. Remember the block sphere visualization. These gates perform rotations of the qubit state vector on that sphere, guiding it through its complex superposition possibilities.
Verbs, I like that analogy. Okay, let's start simple then. Single qubit gates. What are the poly gates and what does the X gate do specifically?
The poly gates are a set of 3 really fundamental single qubit gates, named after Wolfgang Pauli. You can think of them as representing 180-degree rotations. That's pi radians around the X, Y, and Z axes of the block sphere.
Okay, 3 axes, 3 gates.
Exactly. The X gate is often called the quantum version of the classical NOT gate. So if you apply an X gate to a qubit that's definitely in the 0 state, it flips it to the 1 state. And if it's in the Ornco, it flips it back to 0 say. Simple enough.
Like a standard NOT.
Yes, but here's the quantum subtlety. If your qubit is already in a superposition, say, some blend of 0 and 1 day, like H plus 1 dro, the X gate effectively swaps the amplitudes 1 and bay, so it becomes Turo plus Wyjoff. It flips the probabilities of measuring a 0 versus a 1.
Ah, okay. So it's not just a binary flip. If it's in superposition, it's rearranging the likelihoods. Now, you mentioned the Z gate, too. It's called a phase flip gate. What exactly is this quantum phase, and why is it so important?
Right. The Z gate performs a 180-degree rotation, but this time around the Z axis of the block sphere. Now, this one's fascinating because if you apply it to 0 or 1 Oisha, it actually leaves the probabilities of measuring 0 or 1 unchanged if you measure right away in the standard basis.
So what does it do then?
It introduces a phase shift, specifically to the 1 Ors component of a superposition. So if you have Arsh plus 1 Or, applying a Z gate turns it into Ashe minus on Ashe. See that sign change? That's the phase flip.
A minus sign. Okay, but if I can't measure it directly, why care?
Because that relative phase, that plus or minus sign, or more generally, a complex angle, is the absolute key to quantum interference. It's how quantum algorithms work their magic. Think of it like waves interfering.
Constructive and destructive interference.
Exactly. We use these phase shifts accumulated through various gate operations to make the wave functions corresponding to the correct answers reinforce each other, constructive interference, and the incorrect answers cancel each other out, destructive interference. This phase manipulation is how algorithms like Shor's can find factors so efficiently. It's subtle, but incredibly powerful.
That makes sense. You're essentially steering the computation using phase, even if you can't see the phase directly until the very end when it affects the probabilities you can measure.
Precisely. You use other gates, like the Hadamard, later on to turn those phase differences into measurable probability differences.
Okay, speaking of which, let's get to the Hadamard gate, the H gate. Why is this one considered one of the most important gates? This is where things get really interesting, right?
Absolutely. The Hadamard gate is, well, it's foundational. Its main job is to create superpositions. If you start with a qubit in the basic 0 state and you hit it with a Hadamard gate, boom, it's instantly in an equal superposition. A perfect 50-50 blend of 0 oro and 1 rho.
So it's the on-ramp to the quantum realm, so to speak.
That's a great way to put it. It's the quantum computer's primary tool for unlocking that massive computational space offered by superposition. And here's the real kicker. Imagine you have new qubits, all starting nicely in the 0 state. If you apply a Hadamard gate to each of them,
something big happens.
something exponentially big, you instantly create a superposition of all 2 quantum possible classical states, every single combination of zeros and ones simultaneously. That's where the parallel processing power that quantum computers are famous for really stems from.
Wow. Okay, that's a huge leap in computational space right there.
Yeah.
So beyond these polyflips and the Hadamard superposition creator, what about the S&T gates? You mentioned them. What's their role, and why is the T gate linked to this idea of universality?
All right, the S&T gates are also important single-qubit gates. They're primarily phase rotation gates, like the Z gate, but they rotate by smaller amounts. The S gate, sometimes it's called the phase gate, does a 90-degree rotation, or pi2 radians, around the Z-axis.
Okay, a quarter turn.
And the T gate, or the pi8 gate, does an even smaller rotation, 45 degrees, or pi4 radians, also around the Z-axis. Now, the T gate might seem like a small tweak, but it's incredibly important for this concept of universality.
Universality meaning you can build anything with it.
Essentially, yes. It turns out that if you have the Hadamard gate, the CNOT gate, which we'll get to, and this T gate, you have what's called a universal gate set. This means, in principle, any possible quantum computation, any algorithm you can dream up, can be approximated to any desired degree of accuracy using only combinations of these 3 gates.
So HT and CNOT are like the complete alphabet for quantum programming.
Exactly. That's the theoretical foundation. It's the minimal toolkit you need to build anything, which is why the T-gate is so significant. Although, I should add, physically implementing T-gates with the required high precision is actually one of the big challenges for experimentalists right now.
Right. Theory is one thing, building it is another. Okay, so that covers the main single qubit tools. But complex problems need qubits to interact. We need multi-qubit gates. What's the controlled NOT or CNOT gate?
The CNOT is arguably the most fundamental 2-qubit gate. And its primary role, the reason it's so famous, is that it's the main tool we use for creating entanglement, that spooky action at a distance.
Okay, so how does it work? It needs 2 qubits.
You have 2 inputs,
Oh.
a control qubit and a target qubit. The logic is actually quite simple, classically speaking. You look at the control qubit. If the control qubit is in the state 0A, then nothing happens to the target qubit. It's left completely unchanged.
Yeah.
But if the control qubit is in the state 1A, then the CNOT gate applies an X gate, remember, the NOT operation, to the target qubit, flipping its state. So 0 becomes 1A, and 1A becomes 0A on the target, only if the control is 1A.
So the control acts like a switch for the NOT operation on the target. Okay, that makes sense classically, but you said it creates entanglement. How does applying it when the control qubit is in a superposition lead to entanglement? That seems like the core quantum trick here.
This is exactly where the true quantum power of the CNOT shines. What happens if the control qubit isn't definitively 0 or 1, but it's in a superposition? Say, after a Hadamard gate, it's in that 1-2 plus 1A state.
Right, the 50-50 state.
Well, the CNOT gate doesn't just pick one path. It acts on both parts of the superposition simultaneously. So for the part of the superposition where the control is 0A, the target, let's say it started 0A, remains 0A. For the part where the control is 1A, the target gets flipped to 1A.
Ah, so the outcome depends on the control state within the superposition?
Precisely. The final state isn't just two separate qubits doing their own thing anymore. If they started at 0A after H on the first and CNOT, the combined state becomes unOI plus 11OI. This specific state is a Bell state, a maximally entangled state. The fates of the two qubits are now linked. You can't describe one without describing the other. They're one system.
So it's not just two separate superpositions running in parallel. It's a single, shared, interwoven state. That's yeah.
Spooky. Okay, when we combine qubits like this, creating these larger entangled systems, how do we mathematically keep track of it all? What is this tensor product you mentioned?
Right, we need a mathematical tool to handle the scaling. That tool is the tensor product, usually symbolized by a circle with an X inside it. It's essentially a way of sort of multiplying the mathematical descriptions, the state vectors of individual qubits to get a new, larger vector that describes the combined system.
So if one qubit needs 2 numbers, 2 qubits need 4 numbers, and 3 qubits need 8. For n-qubits, the state vector lives in a complex vector space with 2 n dimensions. This exponential growth in the description space is exactly what mirrors the potential computational power. For 2 qubits, the tensor product lets us represent the combined state as a superposition of the 4 possible classical combinations, 0-0 ln, 10-year ln, and 11-year ln.
And this tensor product math is how we capture entanglement, too.
Yes, crucially. An entangled state, like that Bell state 0, 1, 11-year, is mathematically defined as a state that cannot be written as a simple tensor product of individual independent qubit states. You can't just say qubit 1 is in this state and qubit 2 is in that state. The tensor product allows us to describe these inseparable correlated states.
Okay, the math lets us handle the complexity. Now we have gates, we have qubits, we have entanglement. How do we put it all together into a quantum algorithm? Can you explain how to read one of those quantum circuit diagrams?
Sure. A quantum circuit is basically the standard way we visualize and represent a quantum computation. It shows the sequence of quantum gates being applied to a set of qubits over time, usually followed by measurements at the end. Think of it as the quantum version of a classical circuit diagram, like a blueprint.
How do you read it?
You read it from left to right, like text. Each horizontal line, or wire, represents a single qubit. Usually on the far left, they're shown starting in a default state, typically 0 year. Then symbols representing the quantum gates are placed on these wires.
Like the H for Hadamard, X for poly X.
Exactly. If a gate acts on a single qubit, the symbol sits right on that qubit's wire. For multi-qubit gates like the CNOT, you'll see the control symbol, often a dot, on the control qubit's wire, and the target symbol, often a circle with a plus inside air, on the target wire connected by a vertical line.
Okay, so lines for qubits, symbols for gates, read left to right. What about the end?
The final step is usually measurement. This is typically shown by a symbol that looks like a little meter or gauge at the end of the qubit line. This represents collapsing the qubit's superposition down into a definite classical bit, a 0 or 1, that we can actually read out.
That makes the whole process seem much more concrete, actually. Could you walk us through a quick example? Let's build that Bell state circuit you mentioned, 1 is plus 11 here.
Absolutely. It's a great first circuit. Step 1, initialization. You start by drawing 2 horizontal lines representing 2 qubits. Let's call them qubit 0, top line, and qubit 1, bottom line. On the far left, we assume they both start in the 0 state, so the initial combined state is just 0, 0.
Okay, 2 wires starting at 0s.
Step 2, apply Hadamard to qubit 0. We place the H symbol on the top wire, qubit 0. This puts qubit 0 into that equal superposition, 0 zeros plus 1 error. Qubit 1 is still just 0, and so the combined system state at this point is effectively 0, 0 plus 10 errors.
Right, superposition on the first qubit only.
Step 3, apply CNOT. Now we draw the CNOT gate. We put the control dot on the top wire, qubit 0, and the target symbol on the bottom wire, qubit 1, connected by a vertical line.
Control on 0, target on 1.
Now trace the logic through the superposition. For the 0, 0 we're part of the state. The control, qubit 0, is 0A, so the target, qubit 1, which is 0, is unchanged. That part remains 0, 0 air. For the 10-year part, the control is 1 air, so the CNOT flips the target, qubit 1 from 0 to 0. That part becomes 11 air.
Ah, so the two parts of the superposition evolve differently based on the control.
Exactly. The final state is the superposition of these two outcomes, 0, 0 air plus 11 air. That's our Bell state. If you were to put measurement symbols at the end of both wires now, you'd find they are perfectly correlated. You'd measure either 0, 0 or 11 each with 50% probability, but never 0, 1 or 10. Their fates are entangled.
That's a fantastic illustration. It really shows how gates build complexity and entanglement. Now, shifting gears slightly, but still thinking about the overall architecture, there's this profound difference highlighted between classical and quantum computation. Reversibility. What does it actually mean for a process, a computation, to be reversible?
Okay, yeah, this is a really deep and important concept. A process or a computation is considered reversible if you can essentially run it perfectly backward. If you know the output, you can uniquely determine the input that produced it. You can undo the operation without losing any information.
Like running a movie in reverse and getting back to the beginning.
Pretty much, yeah. That's the idea. It's
Yeah.
about information conservation within the computation itself.
Now, you mentioned most classical gates, like AND or OR, are irreversible. Why is that? And why is it considered a problem? How does the reversibility of quantum gates give them an edge?
Right, think about a classical AND gate. It takes 2 input bits and gives 1 output bit. If the output is 0, what were the inputs? Could have been 0, 0, 0, 1, or 10. You don't know. Information about the specific input has been lost, erased.
Okay, yeah, you can't work backward definitively.
And this loss of information isn't just an abstract idea. According to a fundamental principle discovered by Rolf Landauer, erasing information necessarily requires dissipating a minimum amount of energy as heat. Every time a classical computer performs an irreversible operation, it must generate some heat.
Ah, so that's linked to why computers get hot and consume power.
It's a fundamental reason. This heat generation is a major bottleneck for making classical computers smaller and faster. Now, contrast this with quantum computation. With the exception of the final measurement step, all quantum gate operations are inherently reversible.
All of them. How?
Because mathematically, every quantum gate is represented by what's called a unitary matrix. And a key property of unitary matrices is that they always have an inverse. This means for any quantum gate, there exists another quantum gate, its inverse, that perfectly undoes its operation. For example, applying an X gate twice gets you back where you started. The Hadamard gate is actually its own inverse. Applying it twice does nothing.
So you can always reverse the steps, conserving the information.
Exactly. And because no information is lost during the gate operations, this means quantum computation, at least in theory, can be performed with vastly greater energy efficiency, potentially with 0 energy dissipation for the computation itself, excluding initialization and readout. It's a fundamental thermodynamic advantage.
Wow, that's less heat, less power draw, potentially overcoming major classical limitations. Okay, so to kind of pull this all together, how do these pieces, quantum gates, circuits, this principle of reversible computing, form the architectural foundation of a quantum computation?
Well, they really form a very logical and tightly integrated foundation. It starts with the quantum gates. These are the fundamental verbs, the precise physical operations that rotate and transform the states of individual qubits. You have basic flips like the Pauli gates, and then crucial gates like Hadamard that unlock superposition, opening up that vast quantum state space.
The building blocks.
Then these individual gate operations are carefully sequenced and woven together into a quantum circuit. The circuit diagram provides that visual roadmap, the blueprint for the entire computational flow, showing which gates act on which qubits and when.
The structure.
To handle multiple qubits and their interactions, we use the mathematics of the tensor product. This allows us to describe the exponentially growing state space and, critically, to represent entanglement, that uniquely quantum resource created primarily by gates like the CNOT.
The scaling and interaction part.
And underpinning this entire structure is the principle of reversible computing. The fact that the gates are unitary and information isn't lost during the core computation gives quantum computing its potential energy efficiency advantage and fundamentally distinguishes its logic from irreversible classical logic. So it's gates, circuits, multi-qubit math, and reversibility all working together.
It really is an elegant architecture when you lay it out like that, built on these unique quantum rules. Now, one final, really important question for this deep dive. If classical logic gates like AND are irreversible, how can a quantum computer possibly perform any calculation a classical computer can? Doesn't it need to be able to do things like AND? What is the Toffoli gate?
That's a fantastic and critical question that connects everything back. You're right, for a quantum computer to be truly universal, it has to be capable of performing any calculation a classical computer can. So how do we bridge the gap between irreversible classical logic and reversible quantum logic?
Yeah.
The answer lies in constructing reversible versions of classical logic gates. And the most famous and important one is the 3-qubit Toffoli gate. It's also sometimes called the CCNOT gate, which stands for controlled, controlled, not.
Controlled, controlled. So 2 controls.
Exactly. It has 2 control qubits and 1 target qubit. The logic is, it flips the target qubit if, and only if, both control qubits are in the 1A state. If either control qubit is 0 Hui, it does absolutely nothing to the target.
Okay, so it acts like an A and D condition for the NOT operation.
Precisely. And crucially, this Toffoli gate is fully reversible. If you know the output state of the 3 qubits, you can always figure out the unique input state. No information is lost. Even more importantly, the Toffoli gate is known to be universal for classical reversible computation.
Meaning you can build any classical circuit using just Toffoli gates.
Yes. Any classical computation can be implemented using only Toffoli gates, and perhaps some extra ancilla qubits that start and end at 0. So, by showing that we can construct a Toffoli gate using our fundamental quantum universal gate, set the Hadamard-T and CNO-T gates, we prove that a quantum computer can simulate any classical computation reversibly.
Ah, so the Toffoli gate is the bridge. It proves quantum computers are at least as powerful as classical ones.
Exactly. It establishes that crucial baseline capability, showing that quantum computers encompass classical computation before going beyond it, with things like superposition and entanglement for specific problems.
We have truly gone deep into the architecture today. From those basic quantum verbs, the gates, through to the grammar of circuits, the power of entanglement, and this fundamental principle of reversibility, all capped off by the Toffoli bridge back to classical logic. It's a really beautiful logical system built on, well, pretty strange quantum rules.
It really is. Understanding these architectural elements, gates, circuits, universality, reversibility, is absolutely key to appreciating both the power and the challenges of building these machines.
Indeed. And it makes you wonder, as researchers push the boundaries, building bigger and better quantum processors, what totally new forms of computation or information processing might this fundamental reversibility unlock? Things maybe beyond simulating classical calculations or even current quantum algorithms. Something for all of you listening to perhaps mull over.
A fascinating thought for the future.
Thank you so much for joining us on this deep dive into the quantum architect. It's been enlightening.
My pleasure. We hope you enjoyed this exploration of building quantum circuits with gates and logic. It's complex, but hopefully we made it a bit clearer. For more deep dives into cutting-edge tech like this, be sure to subscribe to Tech AI and Beyond.
Thanks again, everyone. We'll catch you on the next deep dive.